Have you ever really tried to wrap your head around infinity? I mean, not just as a word, but as a place? Well, today we're going to check into a hotel that is exactly that. It's a place that will stretch your idea of numbers and, believe it or not, show you that not all infinities are created equal.
Okay, so picture this. There's this massive, grand hotel. But this place is special. It has an infinite number of rooms. Room 1, Room 2, Room 3, and they just keep on going forever. There is no last room. Now here's the kicker. Every single one of those infinite rooms is occupied. The no vacancy sign is shining bright. Now, in our everyday world, full is full, right? No more space. But when you're dealing with infinity, the rules, well, they get a little weird.
So right then, a brand new guest walks up to the front desk and asks for a room. The hotel is completely, totally full. What does the manager do? Turn them away? This is the first great puzzle of Hilbert's hotel.
It turns out you absolutely can make room. And the solution is so simple, it's almost funny. This is our first taste of how our normal intuition just completely breaks down when we start playing with infinite sets. So the manager, this absolute genius, gets on the hotel intercom, and they ask every guest to do something very simple. Please move from your current room, let's call it room N, to the next room over, room N+1. So the guest in room 1 just shuffles over to room 2, the person in 2 goes to 3, 3 to 4, and on and on. Since there's no last room, everyone has a new room to move into. And just like that, abracadabra, room 1 is now totally empty, ready for the new arrival. Nobody got kicked out, but a new room just appeared out of thin air.
Okay, that was a pretty neat trick. But what if the problem gets bigger, like a lot bigger? Imagine an infinitely long bus pulls up to the hotel. And on that bus is an infinite number of new guests, all of them wanting a room. Now what do? That simple N+1 trick isn't going to cut it this time.
The manager doesn't even break a sweat. They just get back on the intercom with a new plan. This time, they ask every current guest to please move from their room N to room 2N. So the guest in room 1 moves to room 2. The guest in 2 moves to 4. The one in 3 moves to 6. You see the pattern? All the original guests are now happily settled into all of the even-numbered rooms. And what does that leave wide open? An entire infinity of odd-numbered rooms, perfectly ready for all the infinite guests from the bus. Problem solved.
So, what is actually going on here? This isn't just a clever story. It's a really cool way to illustrate a deep mathematical idea about how we figure out the size of infinite sets.
The real magic behind Hilbert's hotel is a concept mathematicians call a one-to-one correspondence. It's a fancy term for a really simple idea. Basically, you can prove two groups of things are the same size without even counting them, just by pairing them up. Think about it. If you have a room full of people and chairs, and every single person has a chair to sit in, and no chairs are empty, you know you have the exact same number of people and chairs.
And that's exactly what the hotel manager was doing. With infinite sets, you can't just count to the end, because there is no end. So instead, you create these perfect pairings. If you can make a rule that pairs every single member of one infinite set with one unique member of another infinite set, with nobody left out, then those two infinities are considered the same size.
And this is where it gets truly wild. Using this method, it turns out that the set of all counting numbers, and the set of all integers, including negatives, and even the set of all even numbers, which feels like it should be half the size, right? They are all the exact same size of infinity. This size of infinity has a name. It's called countably infinite, and its symbol is Aleph Null. For a while, it seemed like our incredible hotel with its brilliant manager could handle anything, any group of guests, no matter how big. But then, a new group arrived, and this group was different. This new group of guests, their names aren't simple numbers like 1, 2, or 3. Their names are infinite strings of binary code, like 0.10110 and so on forever. This group represents what we call the real numbers, all the possible numbers you can imagine on a number line, including all the decimals and fractions in between.
And this brings us to the ultimate challenge. Is there any system, any clever trick our manager can come up with to give every single one of these new real number guests a room? Can they create that perfect one-to-one pairing this time?
Well, this very question was answered by another mathematical giant, George Cantor. And he did it with a proof that is so clever and so elegant, it's just mind-blowing.
It's called Cantor's diagonal argument.
Okay, so check this out. Cantor's strategy was brilliant. He said, all right, let's just pretend for a second that you can accommodate all these new guests. Imagine we've done it. We've made a complete list assigning every single real number guest to a unique room. It would look something like this. Room 1 has its guest. Room 2 has its guest, and so on, forever.
Cantor then said, now I'm going to look at your supposedly complete list, and I'm going to construct a brand new number that I guarantee is not on it. And how did he do it? With a simple, beautiful trick. He created a new number by looking down the diagonal of the list. He took the first digit after the decimal from the first number, the second digit from the second number, the third from the third, and so on. So he has this new sequence, made from the diagonal. And then he does one more simple thing. He flips every single digit. Every 1 becomes a 0, and every 0 becomes a 1. And just like that, he's created a brand new real number, a brand new guest.
And here is the checkmate. Think about it. Can this new number he just made be anywhere on our list? Well, it can't be the same as the guest in room 1 because we made sure it's different in the first decimal place. It can't be the guest in room 2 because it's different in the second place. It cannot match any guest on the list because by the way we built it, it's guaranteed to be different from every single one of them in at least one spot.
And what does that mean? It means our list was never complete in the first place. The assumption we started with was wrong. No matter what kind of list you try to make, you can always use this diagonal trick to create a real number that isn't on it. You simply cannot make that one-to-one pairing. The infinity of real numbers is fundamentally, provably, a bigger infinity than the infinity of counting numbers. It's a whole different beast, an uncountable infinity.
This discovery just completely shattered the old way of thinking. It meant infinity wasn't just one thing, it wasn't a single concept. There was a whole hierarchy of different sizes of infinity out there. And get this, it doesn't even stop with just 2 sizes. Cantor also proved that for any set you can think of, you can always create an even larger set just by taking all the possible combinations of its members. It's called a power set. And then you can take the power set of that new, bigger set to get an even bigger infinity. And then you can do it again and again forever. It's an endless ladder of infinities, each one so much bigger than the last, it's hard to even imagine.
Which brings us to the final, absolutely mind-bending thought. Our journey started in a hotel that seemed impossibly big, yet it couldn't handle certain guests. It's shown us that infinity isn't some single destination. It's an endless, fascinating, and paradoxical journey upward. So if there's truly an infinity of infinities out there, the real question isn't just how big it gets. The real question is, does it ever end at all?